All right, well, apparently this is live. I am going to keep the earpiece in for the first 30 seconds, so I know that I'm not doing horrible things to everybody's eardrums with really messed up sound, and then I will lose them. Cool. Everything seems good. So, greetings to anybody from Mount to Sales. This entire demo is basically for you. So, what I'm going to do is hang out here, do a couple of problems, and hopefully somebody will show up and ask a question, poke around a little bit, and then you can let me know what you think. So, losing the earpiece. Which is nice because then I don't have to hear myself on delay. I made a note in the email, but the one thing, if there were anything that I could fix, it would be that the gods of the internet allow streaming to be done without quite so much buffering. Right now, it makes sense trying to keep the audio and the video and everything synced up. They don't know what kind of internet connection I have. They don't know what kind of internet connection you have. They're trying not to have everything stop and buffer. So much like live TV, there's about a 10-second delay. Now the chat function that is underneath the actual watch video is pretty darn near instantaneous. If you type something and you hit enter, I will see it on my screen. The only issue is that it is delayed in the sense that my response to you is only going to get to you 10 seconds after I say it. So as opposed to trying to actually have a conversation with me back and forth, it is normally easier if you just type in any questions you have, type in any comments you have, just let fly, and I promise I will get to everything that you have a question about before I move on to another question. So basically, I'm now going to sit here for a couple of hours and do math problems of my choosing until hopefully somebody shows up and asks a question in this particular live stream. So normally a bunch of other questions going on. I have other people taking care of that today so that I can focus on you guys. But at the moment, there are no questions for me to answer. So what I'm going to do is just pick a problem or two and show off what this can do in terms of, you know, what happens on the screen, what you can see, all that fun and incredibly exciting math tutoring stuff. So I've already got this giant trig identity up here. I'm going to get this out of here and we'll take a look at something else. So let's pick a problem here. Go with something out of algebra. And how about, for giggles, systems of equations? We'll do solving by substitution. And we'll do a kind of bothersome one. Okay, so we start with the following system of equations. We've got 3x plus 5y equals 11. And 4x minus 3y equals 5. Now, if we want to do this with substitution, which is how we're going to do this, because it's how I've decided we're going to do this and how this problem was written, unfortunately, what we need to do is we need to take one of these equations and isolate one of the variables. So let's begin by taking our first equation here and let's try to isolate x. So we've got 3x plus 5y equals 11. To start out, we can subtract 5y from both sides of the equation. And now just by convention, I'm going to leave the y, I guess the term with the y in it in front of the term that's just a constant. So we'll end up with 3x is equal to negative 5y plus 11. And from here, we need to divide both sides of the equation by 3. So we do that, and that will leave us with x, which is what we were looking for, on the left-hand side, and this horrible fraction that probably makes it seem like we've done something wrong and we shouldn't have gone in this direction, but I promise it will all be okay in a minute. So, all right, cardinal sin, I bumped the microphone. I apologize because I don't have the headphones in, but if you do, that is going to sound pretty awful. So now we've used our first equation, we've solved for a variable. We need to take our second equation and plug that variable back in. So it's really important that we not mix up equations when we do this. That's one classic error. People take one of the equations in the system, they solve for a variable, and then they plug it back into that same equation, and you end up getting a true statement. You'll get something like 1 equals 1 or x equals x, but it doesn't help you in any way solve the system. So whatever equation you isolated in, you need to use the other equation to substitute. So we've got x being equal to that. So we can plug that in our second equation, and we'll have 4 times this giant monstrosity minus 3y equals 5. Now, it might be tempting in the beginning here to multiply the 4 through. The easier thing to do, because we know we really want to get rid of this 3 in this fraction, these big fractions like this make for really messy algebra. The first thing we're going to do is multiply both sides of the equation, every term in the entire equation, by 3, and that will cancel out that denominator. So the entire left side of the equation, you'll multiply by 3. The entire right side of the equation, we will multiply by 3. And now what that's going to do, here in our fraction, it's going to cancel out that 3 and that 3, and then we just have to continue multiplying until we get to the negative 3y. So for starters, we end up with 4, not if I'm on the wrong layer, we don't. We end up with 4 times that negative 5y plus 11. That's going to be minus the 3 out here times the negative 3y, so negative 9y, and that is going to equal 15. 5 times the 3 on the other side. From here, we can distribute this 4 through the parentheses. So 4 times negative 5y is going to give us negative 20y. 4 times positive 11 is going to give us a positive 44. And that is still minus that 9y, and that is still equal to 15. From here, we can combine like terms. We have negative 20y and a negative 9y. So that can combine to give us negative 29y. It'll still be plus 44 and still equal to 15. Now we want to try to isolate y. So we can start by subtracting 44 from both sides. And this, conveniently enough, is going to give us negative 29y is equal to negative 29. which when we divide both sides of the equation by -29, gives us the first part of our solution. Now move everything around here just a hair, so we have some room. I say again, gives us the first part of our solution, y is equal to 1. And now that we know what y is equal to, we can take that information and plug it back into either of our original equations and figure out what x is. So completely arbitrarily, I'm just going to plug it into the first one. So we have 3x plus 5 times what we know now is 1. We can plug that in. It's going to equal 11. Going to be 3x plus 5 is equal to 11. We can subtract 5 from both sides of the equation. And we'll end up with 3x is equal to 6. Divide both sides by 3. And we end up with x is equal to 2, which is the other half of our solution. So that is a long, drawn out, and hopefully not too messy example of solving a system of simultaneous equations with car noise in the background by using substitution. So hopefully, again, if you're watching, you can see a little bit of how this works, how this would come across. I'm of two minds when it comes to answering questions that a student posts exactly, or trying to come up with a similar enough example that it will be helpful enough that they can get through the question that they have. On something like this, because this is a fairly complicated simultaneous equation to solve by substitution, this might be something where I'd be willing to take the question at face value and work through it with a student if they were there and chatting. If it's a question that is a little bit simpler or has more easily mirrorable mechanics, then you just come up with a question that mirrors that, and you wouldn't have the answer to your question, but as in you wouldn't have the solution precisely to your math homework, but you would be able to see an example that works exactly the same way. And if you're on the chat, even if you're on the chat much later and you've taken this information, you've gone through and done the problem, and you say, hey, just wondering, is the correct answer y equals 1 and x equals 2? I will let you know what the correct answer is supposed to be. Presumably, your teacher is going to want to see some amount of work, and if you have worked that out to the correct answer, I am not going to keep you from that. It's not very helpful for me to say there will be no possible revelation of any answer, because it's not really the point. And to me, it's not really the point of homework either. I'm not here to do a student's homework, but I am more than happy to help a student with a particular problem if it's something they're struggling with and they're willing to go back and forth a little bit. So there's one problem. Let me get rid of this one, and let's see if we can't find ourselves another one. So how about we did a little trig already. How about some calculus? So yeah, let's find a derivative using the definition of the derivative. Always a good idea. So let's find f prime of x. Given that f of x is equal to x squared. So if we're going to use the definition of the derivative, it might be helpful to have the definition of the derivative. So we're looking at, we'll keep it all in black for now. The derivative of a function is equal to, the limit as h approaches 0. Really important, we have the limit as h approaches 0. If you have a good teacher, they will take your head off if you leave out at any point in the problem the limit as h approaches 0 of f of x plus h minus f of x all over h. So, given this, we have a couple of pieces that we need to know in order to plug them in and in order to solve for the derivative. So, first, we need to know what f of x is, and we're given f of x in the problem, so that is extremely helpful. We know that f of x, which is not a box, f of x is equal to x squared. And I do want to keep that up in case there are any questions. Now we need to figure out what f of x plus h is. Now the way this function is set up, we have f of x equals x squared, which is essentially f of whatever you put inside here. I want you to take it and square it. So that's what that function is telling us to do. The x is just a placeholder here. So for f of x plus h, well now x plus h is inside the box. We are looking at x plus h squared. Now we're going to have to do a little expansion here. That's x plus h times x plus h. And if we FOIL this out and combine everything together, we will get x squared, xh, hx, and both of these are the same thing. 3 times 5 is the same as 5 times 3. Just if you're thinking about foiling it, you'll get a different order, but they're both the same type of term. And then plus h squared. So this is actually going to come out to x squared plus 2xh plus h squared. So now we have our two pieces. We can plug these into our equation, and we'll be good to go. So the derivative of this function is going to equal the limit as h approaches 0 of, and now we can plug everything in, x squared plus 2xh plus h squared minus x squared. And a good way to tell if you've done everything correctly is every term in the second piece that you're subtracting here should have a matching term that it cancels out with in the first equation that you come up with. So in this case, we've got an x squared and an x squared, so we can cancel those out, and that is going to leave us with a limit as h approaches 0 of 2xh plus h squared, because these guys here cancel each other out. So they're gone. Now what we can do is divide that h into each of these. So we'll have the limit as h approaches 0. Now 2xh divided by h, the h's cancel. We're just left with 2x, and positive h squared divided by h will just end up being h. We lose one of the squares, that's just h times h. That divided by h leaves you with h. Now, the reason that we couldn't apply the limit in the beginning here, we have this limit as h approaches 0. The reason we couldn't apply that up to this point is we've always been dividing by h, and we are not allowed to divide things by 0. The universe gets very, very upset with us. So we've done all this work so that we could divide that h out, get it out of the denominator, and now we can apply that limit. So what is this 2x plus h getting closer and closer to as h gets closer and closer to 0? Well, h getting closer and closer to 0 is just the h canceling itself out here. So as h approaches 0, this gets closer and closer to 2x. And so we end up with our solution, which is that the derivative of x squared, using the definition of the derivative, ends up being 2x. And we're good to go. So again, I believe if I heard correctly, at least one person who might be watching is in Calculus 2. So a throwback to things you probably don't ever want to think about now that you have the power rule and the chain rule and all those wonderful rules and trig derivative definitions, so you don't have to mess with this. And I think one of you hasn't even touched calculus yet, so also probably not incredibly helpful, but again, just as an example of how this can work, and basically just that I have some idea what I'm talking about. I am a big fan of the use of color, and the purposeful use of color, not the use of color just to make it pretty and aesthetic, although I do think there is something to be said for aesthetics in math, but more the use of color to illustrate where something's coming from, why it got plugged into the place that it got plugged in, how it got canceled out, when it got canceled out. So big on color, big on transparency, big on some semblance of order to the math as well. A lot of students, if they're struggling, a big part of that is keeping everything in line and then really realizing why we're doing something. Sometimes it is for the sake of simply solving the math problem, but there is a reason why each of these little procedural steps happens. There is a reason why we can't just take the limit at the beginning of the question, because the way the definition of the derivative is set up, you have a denominator that just has h in it. And so most of the time when you're trying to solve these things, you end up with having to manipulate the numerator in some way or manipulate the entire fraction in some way in the case of some of the square root definition of the derivatives, such that you can get the h out of the denominator. That is kind of the idea. So again, probably not actually functionally helpful to anybody. Won't know what's functionally helpful unless somebody posts a question, which I'm hoping somewhere maybe 6 or 7 o'clock would be awesome. Someone will end up being home, and maybe that'll help. But in any case, I'm gonna pick another problem, see what we can do. So, keeping in the calculus state of mind, all right, how about some implicit differentiation? That is always fun, he said. not sarcastically in any way at all. So let's find dy dx. We're going to use implicit differentiation, and we're going to find dy dx for, let's go with y cubed minus 8xy. Sorry, I have the example problem sitting on my other computer. I have to glance over until I get the whole problem written out. There we go. So we're going to find dy dx for that equation using implicit differentiation. So the way we're going to do that to begin is we're going to take this whole thing, drum roll, and take the derivative of all of it, every last bit. So, whoa, I don't think I clicked on that one, but we'll see. I wanted something a little less dramatic than red. So what does this amount to? Well, it amounts to taking the derivative of each one of these pieces individually. So the derivative of y cubed with respect to x, again, we're finding dy dx. And now here, this gets a little tricky. I am a big fan of leaving the addition and subtraction signs outside of the derivatives. I think it makes life a lot more straightforward. I know people who are not as big a fan of that, and I am totally open to that option. But for me, as long as you remember that these brackets are here, or parentheses or whatever you want to use are there, this to me makes a lot more sense. I don't know why I keep clicking on that red when I mean to click on the gray. Makes a lot more sense than doing it the other way. We'll have 3 prime minus x squared prime. Now we're taking derivatives with respect to x. So everything that we do here is going to have a dy dx or a dx dx next to it somehow. So the derivative of y cubed with respect to x is, first we deal with this derivative just like we would any other power rule derivative. So we say this is the same thing as 3y squared, but now we need to incorporate the fact that this is a y that we're taking the derivative of with respect to x. So we have to tack on a dy dx onto the end of that. And we'll leave all of this in these nice neat brackets. Now with 8xy, we actually have a product rule that we have to deal with. So we're looking at the derivative of the first times the second plus the derivative of the second times the first. That's going to be its own whole mess. And then that is going to equal the derivative of 3. Thank you. It's nice and easy. Constants just become 0. And then the derivative of x squared is going to be 2x. And I'm going to write this anyway, even though it immediately cancels, because it's good, I think, to think about with all implicit differentiation. Every time you've done a derivative, even though you haven't realized it, you've been exceptionally lazy. When you've taken a derivative with respect to x that had an x in it, you didn't write dx dx. Now the reason you didn't do that is because the change in x over the change in x is just 1. It's always 1. It always cancels back out. But it is helpful for our purposes to remember that anytime you take the derivative of anything with a variable, you end up taking a look at the rate of change of that variable over the rate of change as it relates to x. So hopefully this doesn't make this more confusing, but the same thing as normal. X squared would normally be 2x, but there's a dx here that I'm going to write and then immediately cancel out once we're done expanding this all out. But just so you're thinking in that realm. So y cubed, 3y squared, just like normal, but dy dx. X squared becomes 2x, just like normal power rule, but it's multiplied by dx dx. So let's keep this going. We'll have our dy. That's a really ugly looking dy there. Dy dx. Now we have to actually take care of what we're dealing with here. So the derivative of 8x is just 8 times dx dx, because I'm being super OCD about writing all of these out. And that would be times y. And we're adding that to the derivative of y, which is just 1. Then because we took a derivative with a variable, we stick in dy dx. And that's going to be multiplied by 8x. Again, we're subtracting this whole thing. It's really important, as bulky as this gets, it's really important that we keep the parentheses and the brackets in order so that we know where they are. And then this is minus 2x times dx dx. I'm going to pick this up and move it over so everything is in line. There we go. So where does this leave us? Well, the dx dx's can cancel. They can go away because we know the change in x over the change in x is just going to be 1. Everything else we have to keep. So we have 3y squared times dy dx minus, now here we have 8, the dx dx cancels, times y. We're subtracting all the way through these brackets, so this is again minus, now this is 1 times dy dx, we can't cancel the dy dx, and we have an 8x, so we'll say 8x times dy dx. I'm just putting the dy dx's second when they're in a term or at the end of the term so that they're easier to deal with and they all look the same. And that is going to equal just negative 2x. So now in order to figure out dy dx, in order to isolate this, we want to get everything, every term that has a dy dx on one side and every term that doesn't have a dy dx on the other side, so we can factor out dy dx. So the only term that doesn't right now is that negative 8y. So what we can do is add 8y to both sides of the equation. And so now we have 3y squared dy dx minus 8x dy dx and that is going to equal, we'll keep the x on the left just for convention here, negative 2x plus 8y. And I keep drawing everything farther to the right or left than I should. I need to keep moving it back. Okay, so now all of the terms on the left side of the equation have a dy dx in them. What we can do is we can factor that out. We can divide dy dx out of both of these terms and stick it in front of them, leaving them in parentheses. So this is going to give us dy dx times 3y squared minus 8x. And that's going to equal negative 2x plus 8y. And now we can divide both sides of the equation by that 3y squared minus 8x. It isn't pretty, but it doesn't have to be, because all we need to do is isolate dy dx and we're good to go. So divide both sides of the equation by 3y squared minus 8x. And we will end up with our final answer, which is that dy dx is equal to this slightly monstrous but totally finished negative 2x plus 8y over, we'll bring the x to the front again just for the sake of keeping everything the same, negative 8x plus 3y squared. And that would be our final answer. So that was fun. A longer problem, obviously a little bit more involved problem. A lot of these as well, and this is another, I think, very valuable aspect of the site. A lot of questions like this are already solved, worked out on video with explanation on the site itself. So if you have a general question, there's a lot of resources. If you need a replacement for what should have happened in the classroom or what generally happens in the classroom, you're looking for a replacement for a lecture, there's a whole bunch of places you can go that are fantastic. If you're looking for something that will cover what a tutor would actually do, or one-on-one help, if you're looking at a specific type of question and you have a problem, you can absolutely ask and watch and go back and forth and chat and make sure you understand what's going on. You can also, at any time you want, watch any of the videos, and there are 1,020, I think, videos, various speeds, various learning styles. Admittedly, the audio could use a little work. It was my first foray into audio design and recording. So I apologize for the audio, but the videos in general are really, really good and really clear. If you have a question, you can go through search and say, how do I factor a polynomial now that the lead coefficient isn't 1? Enter. And it will pull up any relevant videos that deal with that question. You can just go through by subject and topic and subtopic and look at algebra, polynomials, solving polynomials, factoring polynomials with non-1 coefficients, and pull up examples from there. So in addition to having this as a resource where you can ask and then wait to get a response and then go back through and type, you also 24/7 have access to all the videos, which are very specific mechanics-driven videos. Again, I apologize for the motorcycles. There seems to be a herd of motorcycles behind me today. A whole string of mechanics-driven, procedure-driven, specific example videos, as opposed to, generally speaking, what is the power rule and how does the power rule work? Well, no. Here are the 7 permutations of the power rule. If you can do these, you will be fine on a test. That is the sort of thing that this site is trying to take care of. If you have no idea about a topic, again, it's sort of akin to what would you call a tutor to help you with? And it's possible, if you had one-on-one time with a tutor, you could go through and learn a topic from scratch. But for the most part, this is designed as somewhat supplemental. I'm assuming that you've had a lecture, You may have walked away from that lecture completely clueless, but at least you've heard of something before. I am not going to be incredibly useful depending on the topic. If it's something like the power rule, I can introduce that in a couple of minutes. But depending on what's going on, if you've never done implicit differentiation before, this is probably not the place you want to start doing implicit differentiation. But if you've seen it once, even if it made absolutely no sense, we can hammer away at it until it makes good sense. Or again, you can watch the videos, you can try doing the problems in the videos yourself, and if you can do those, you are pretty much ready to deal with 99% of what's going to get thrown at you regarding that topic. So that is the idea. I am going to know if I can take a quick break or not. I'm going to pause the stream on my end, and if anybody has any questions, feel free, type, go crazy. The stream should just say it's been interrupted, which should be fine. And I will be back in 5 minutes and just keep working along at problems, and we'll see what we can do. So enjoy, and I'll be right back. Okay, back for 2 seconds because I ended that last stream making an incredibly ridiculous face, and I'm not going to stare at that face for the next 5 minutes while I get stuff done. So I have no idea how, I guess, not to make an incredibly ridiculous face, but I'm going to do my best. So internet, farewell for 5 minutes. I will return in just a moment.